Okay, this is a quick video about entropy and the second law of thermodynamics. If you've probably talked about entropy before, you've probably talked about like broken eggs or messy desks or something like that, and we'll get to that later, but really we want to start more basic, and it's going to be a little bit mathy, this video. So the first thing we need to understand before we can understand what entropy is state functions. Entropy is a state function. What does it mean for something to be a state function? Well, examples of state functions are pressure, temperature, volume, energy, number of particles. And why are they state functions? They're state functions because I can just look at the gas. I can just look at it in an instant of time, and I can tell what's the temperature of the gas. I just stick a thermometer in and it tells me. What's the volume? I can measure it in an instant of time. I can look at the energy. I can look at the number of particles. I don't need to know how the system got this way in order to understand what those are. Those things are things that I can just measure. It doesn't matter how much time and energy it took to set the system up. The system is what it is. These are state functions. I could change the state of a system, and that would change the state functions of a system. So I'd go from P1 to P2, so on and so forth. So that's what a state function is. It's something you can tell about a system just by looking at it without knowing anything about the history of a system, right? In fact, we even have equations called equations of state. So these are equilibrium states, and they relate state variables of a system that you can just look at and know everything you need to know about a system. What if you wanted to know the change in a state variable? Well, that's easy. You know V2, you know V1. If you want to know what the change in volume is, that makes perfect sense. You just take V2 minus V1. If you have some complicated process and maybe you know how the entropy changes differentially, okay, great. Here's dV. And dV, this is just direct application of chain rule taking a derivative, basically. And this is called an exact function. That's going to be important because I'm going to show you something in a second that is an inexact function and how this relates to state variables. But something to notice here is that if I do with the ideal gas law, so here I took the ideal gas law, and I took this definition seriously, I plunked in all these things, there's actually a very special relationship between all the coefficients of these dp, dt, and dn's. And if I write it as mdp plus ndt plus qdn, which is how math books like to write it, what you will find invariably are relationships like this. dm dn equals dq dp, which just sounds like alphabet soup. But really what they're saying is, look, this term is dv dp, and this term is dv dn. And what they're suggesting is that I differentiate this term with respect to p and this term with respect to n. And so what do they become? They become mixed partials, but they're equal mixed partials. So of course they're equal to each other. This is like a no-brainer. Obviously, if you take mixed partial derivatives, you're going to find that they're equal to each other. And so you say, well, isn't this true of every single function you could possibly imagine? Well, perhaps, but the other question is it possible to write the differential of something and find that relation to not be true? And then what does that imply? So let's see, what is not a state function? Well, a good example of something that is not a state function is work and heat. Maybe you've heard this before. What does that mean? Work and heat are not state functions. Well, one of the things we said about state functions is that a state function depends on an initial and a final, if we're interested in the change in those two. Notice I didn't say anything about how I get from P2 to P1. I just have to know what P2 and P1 is. That means that state variables are path independent. State variables are path independent. Well, what does that have to do with work and heat? Let's just think for a moment about what work is. Everyone knows work is the integral of PDV, which is the area under the curve. I start at some point A and I go to some point C, but notice I've decided on two different approaches to get there. I could go AC, which is a direct path, or I could first go to B and then, I don't know, take this curvy path down to C. These are arbitrary. The important thing is that it's pretty clear that there's different areas under both of these curves. For AC, here's the area. For BC, it's this bigger area. This is just pretty visually obvious that the area under these two different paths is different, and therefore we can say that the work going between these two paths is not the same. What does that mean? That means that this is path dependent. That means in some sense delta W has no meaning. There's no work at C, there's no work at A. I can't say the work at C minus the work at A. This is nonsense. It's nonsense. And because it's nonsense, sometimes you'll see it written in a funny way. You'll see it written like this. They'll write a delta W with a lowercase delta instead of dW. Sometimes you also see this written as d/W because it's an inexact differential. And this is just our way of reminding people, hey, this is not a property of the system that you can measure. It's a property of a process, not a property of the system at any given point. Okay, so what does all this have to do with the derivatives and stuff we were looking at earlier? Well, let's examine dq instead, and let's just see if dq can be a state function. In other words, some small amount of heat added to the system. We'll say it's a state function if I could say q2 minus q1 is in some way equal to delta q. Okay, we'll see if that statement is meaningful. Okay, so the first thing you do, rewrite dq in terms of other things. So if I have the ideal gas law, the energy of the system always depends on the degrees of freedom, and the work is always PDV. We do another thing. We plug in by ideal gas law, P equals nRT over V. Okay, and now look, we're in the same position we were at before. I have some differential function, which has something in front of the dt and something in front of the dv. And now let's just see if this thing that's totally obvious is supposed to be true. You'll find that it isn't. Differentiate this guy with respect to v. So d by dv of f over 2 nr is 0. And then let's do d by dt of this. D by dt of nRT over v. That's nr over v. Holy Toledo. These are not the same, which means this is in some sense a broken function. This is inexact. And it's the same thing as W. The fact that this is broken, we cannot say Q2 minus Q1. This is also path dependent. Path dependent, meaning Q is something that refers to the path, not something that refers to the gas at any given state. It's not a property of the gas at all. It's not a state function. The question is, though, like, is there a way that you can fix these? Maybe we shouldn't be talking about heat and we shouldn't be talking about work. Is there some way to take our formula for Q and fix it? Well, if you remember, the problem with Q was that one of the terms had a T in it and it didn't make the differential go away. So what happens if let's just divide by T. Maybe that'll fix it. If I divide by T, then I end up with something that looks like this, and I can plug in, same thing I had before. And now notice this time, because I'm dividing by T, there's no T in this term. That means, holy smokes, if I write it this way, I've just created a state function. It took me 2 seconds to create a state function. And I did it from something that isn't a state function. So this weird combination, dq over T, is apparently a property of the gas. And let's call it S for state, because it's such an important state property, right? Of course, I have absolutely no idea what this thing is, but it is a property of the gas. It's a property that, in principle, I can measure. And I just need to look at the gas. So what's delta S? Delta S is the integral of ds, and that gives me something that looks like this. Okay? If I pop off that integral, I end up with a formula for S that looks like this. This is only true for an ideal gas, and I'm holding like the number of particles constant and stuff, just because I didn't want too many terms. But this is the idea. You have an ideal gas, and the change in this state property, we don't know what it is, but apparently it's given by this formula. So let's look at a quick example. Let's say I have a mole of diatomic gas, and it's heated isobarically. Isobarically. So if you remember, that means the pressure is constant. It's heated at constant pressure from 350 to 500 K. I want to know what the change in entropy is. And you might be thinking, there's so much information you're not given. I agree, but don't let what you don't know prevent you from writing down what you do know. You're told it's isobaric, and you're told the initial and final temperatures. Somehow we're going to use this. The problem is I don't know V final and V initial. But I do know that it's an ideal gas. And for an isobaric process, V final over V initial equals T final over T initial. Just to convince you of that, P in general is nRT over V. But P1 equals P2. So this is nRT2 over V2. I write ones over here, and voila. you get that relationship. Very straightforward. I don't suggest you should memorize stuff like this. I suggest you memorize the ideal gas law and then know what isobaric means instead. Okay, so great. If I have that relationship, I can just bang out this problem. I literally just plug the numbers in and, okay, I get some number and it's 23 and change joules per Kelvin are the units for delta S. So I guess energy per degree tells me something about what this state quantity is, but I still don't have a firm handle on it. Now, the thing that you might notice, some of the more observant of you, is you might say, hey, wait a minute. This looks like CV, the specific heat of a gas at constant volume. And if you add this to it, plus R, this whole thing is actually CP times log T final over T initial. Isn't that interesting? We have the specific heat at constant pressure, and that somehow tells us something about the entropy of the system. And you might say, wait a minute, we've been using ideal gases the whole time, but could we do this with solids? Like, we know that for a solid, if you add heat to it, you see a corresponding increase of MC delta T, or you could talk about moles for a solid as well, NCV delta T, or NCP delta T. Let's apply our definition of entropy to a solid and just see what happens. I will say, though, before we do that, one thing to notice is that this is a positive quantity. Maybe you've heard the second law of thermodynamics, entropy always increases. Obviously, we didn't prove it. This is just one particular problem. But let's look at another one. Okay, let's say that we can apply this to a solid, okay? And let's say that I have two solids, a hot solid and a cold solid. Now you say, what happens if I put these two solids together? Well, if they're the same size and they're made out of the same material, we know exactly what's going to happen. It's going to turn into some lukewarm combination of the two. And I would just ask you to pause and think for a minute. Why does that happen? It certainly doesn't have to. There's nothing in conservation of energy that requires the two to come to the same temperature. It's just something that we observe about the universe. Hot things get cooler, cool things get hotter. But there's no driving principle behind that other than that's just our experience with things. And so let's calculate what the entropy change looks like for a process like this. Well, on the left, the entropy is still dq over T. That's how entropy is defined, right? And so for our block, it's the number of moles times the specific heat times dt over T. You integrate it, you get something that looks like this. On the right, for the cold one, we do the exact same thing, except now we just have different initial and final temperatures. You'll end up with something that looks like this. The key thing to know here, and this is really interesting, is if you punch this up on your calculator, you'll find that it's actually less than 0. This block loses entropy. And if you punch this one up on your calculator, you'll find out that this one gains entropy. This one gains entropy. And so you might think, wait a minute, I thought the second law of thermodynamics said you have to gain entropy no matter what. But that's not what the second law of thermodynamics says. The second law of thermodynamics says that in any naturally occurring process, what you do is you add up all the entropies of all the things involved. And what you find is that at the end, you have a bigger number than you started with. So let's do that. Let's see what that looks like. If you add up all the entropies, you end up with a thing that looks like this instead. So I'm just adding this number to this number. And if you punch this number up on your calculator, you will find that it is indeed greater than 0. So the second law holds here too. I don't pretend that I've proved the second law of thermodynamics to you. In fact, there's no way to prove the second law of thermodynamics. All we can say is that it's consistent with our experience that every single naturally occurring process we look at, the entropy is this thing that tends to grow. Bigger. This is really curious because we just made this function up as a mathematical trick. It's a property of the gas. I don't know what it is, but apparently the way things work in the real world, this property has to always increase. That is amazing. And that's why it's the second law of thermodynamics. It's like a fundamental principle of the universe that this quantity, which we don't know what it is yet, seems for any naturally occurring process, things that happen on their own, hot getting cold, cold getting hot, cold getting hot, that it seems to make this state variable get bigger. Okay, so this is the second law of thermodynamics. So what we're saying is that this system that we drew before, in addition to having all of these state variables, also has a state variable S. In other words, it's some property of the system. I can glance at the system, I can measure it, And if the system changes, this state function is going to get bigger. No matter what I do to it, this function is going to get bigger. Of course, I still don't know what it is. And moreover, what does any of this have to do with broken eggs and messy desks and all that? And that I will explain in the next video.